Equilibrium is the concept of balance between products and reactants. However, which side is more favored, one or the other, is dependent on the equilibrium constant. This equilibrium constant is specific for each different reaction and is temperature dependent. This experiment focuses on developing and calculating the equilibrium constant for the reaction or the balance equilibrium of cobalt tetrachloride and the cobalt hexaquo complex. The balance between the cobalt ion bound to 4 chloride ions to form the cobalt tetrachloride complex, or bound to 6 water molecules to form the cobalt hexaquo complex. It's the balance between these two that allows you to see the differences between them. And later on, you can see that it's temperature dependent, and you can figure out with the concept of heat and thermodynamics whether energy and heat is either a product or a reactant.
This experiment focuses on looking at the concept of equilibrium, and specifically the equilibrium of cobalt chloride. So previously, looking at the Le Chatelier's principle experiment, that was a qualitative experiment. You were looking at which direction the equilibrium is going to, either products or reactants. This experiment is a quantitative experiment. You're looking at how much of the reaction is going towards the products versus the reactants. What is that ratio? In the end, when a reaction is in equilibrium, that means it's not really happening anymore. The products and the reactants are balanced at a balanced state. But what is that ratio? How much product is there and how much reactant is there under those equilibrium conditions? And the equilibrium constant is the specific ratio that determines how much of each of the components is present in the reaction. So the chemical equilibrium constant really is a ratio of products over reactants, but it's also based on the stoichiometry of the balanced chemical equation. So equilibrium is based on concentration. If something is more concentrated or less concentrated, that will have an impact on the reaction itself and which direction that it will shift. So when calculating the equilibrium constant, this specific ratio, you're looking at the concentration of each of the individual components raised to the power of its stoichiometric coefficient. So it's still products over reactants, but you're taking into account the different ratios that they react with in the balanced chemical equation, as well as their concentrations to begin with. There are a lot of different types of equilibrium. The basic formula is the same. It's still products over reactants, and usually any equilibrium constant can be written as K E cubed, just meaning the equilibrium constant of the equation. But that's really for anything. There are a number of different ways to write that K with a different subscript, and that different subscript just means the type of reaction it is. So Kw is a very specific constant. That is the equilibrium of water itself. So water is in constant equilibrium with H+ ions and hydroxide, and this unique equilibrium is so important, especially in acid-base chemistry, that it has its own subscript. So Kw is the constant of the equilibrium of water. Ka and Kb are based on dissolving acids or bases. A Ka value is the equilibrium constant of an acid dissociating into H+ and its counterion. A Kb is the equilibrium constant of a base breaking apart into its individual components. There are two others. Formation constant, which is what this experiment looks at. It's the equilibrium between of the formation of a complex ion, which I'll go over a little later. And then for solubility, Ksp. This is referred to as the solubility product because it's the equilibrium of the solid salt dissolving. So the solubility that you've looked at before, looking at solubility data, this is related to the equilibrium of that solid salt and how much it's able to break apart before you can no longer dissolve anymore. And it's called the solubility product because when you're looking at a K value, when you're calculating these equilibrium constants, you'll notice that it's based on a concentration. So that means if it is a pure solid, there is not really a concentration associated with the solid, so its value would just be 1. There is no concentration. In Kw right here, water is liquid and a pure form. It's just itself. It doesn't have a concentration specifically. So, or at least in terms of the reaction and the equilibrium, so that is a value of 1. The same would be true for any solids. The concentration of the solid in the equilibrium constant would just be listed as 1 because you can't have a specific concentration of a solid. And because of this, the Ksp is just the product of the concentration of the individual ions. One way to look at equilibrium and going through these equilibrium calculations are ICE tables. And ICE refers to initial, change, and equilibrium. And I will go over this a little bit later, but just to kind of introduce you, the initial concentration is what would be present if the reaction never actually occurred. If time was paused, you mix everything together, and before the reaction takes place, what would be the concentration of each of the components in that test tube or in that beaker? That's the initial concentration. However, you can't pause time, and the reaction itself, because of any changes and because of Le Chatelier's principle, will change the concentration in one direction or another. It will either add concentration or remove concentration from the products and reactants. And the stoichiometry plays a role in that. Depending on what the balanced chemical equation is, that will dictate how much of a change occurs. And finally, equilibrium. So this is the concentrations that you're actually measuring. If you go in a flask, a beaker, test tube, and you're measuring a concentration or you're measuring something, that is in equilibrium. The reaction has kind of finished and it's in that balance state, it's equilibrium state. So to figure out how much the starting concentrations are or how much the change is, you're using this measured equilibrium concentration and you're overall finding these different components. As mentioned, this experiment focuses on the equilibrium of cobalt chloride, and it's two different complex ions. So you're going to be watching this video and looking at the differences in this chemical equation here. So looking at the two different complexes, there is the cobalt ion bound to 6 water molecules, and that will give a red color. There is also the cobalt ion bound to 4 chloride ions, and that will give a blue color. This is where the intense color cobalt blue comes from. This is only present, though, or only visible in the absence of water. Water itself is part of this equilibrium reaction. And when water itself is part of the reaction, it can be looked at in a couple of different ways. You're seeing how water reacts and the equilibrium between the red component and the blue component. And this is where solvent selection can be very, very important. So solids can dissolve not only in water, but in other solvents as well. And in this case, in this example, the cobalt chloride is being dissolved in ethanol. And when it's dissolved in ethanol, you get the dark blue, cobalt blue color because there is no water or very little water present to drive the reaction towards the red color. But if you dissolve it in pure water, it's going to start out as that red color. There's an abundance of water. And when you're looking at something and choosing a solvent, especially when that solvent can be part of the reaction, it drastically changes the equilibrium of the reaction. And it's based on these kind of conditions. So here's an example of copper binding with ammonia. And water is part of this reaction. When you have the reaction in water, water is the pure substance, it's the solvent, it's everywhere. There's so much of it that the concentration is irrelevant. So because it's the pure substance, you have the product concentration of the copper tetraamine divided by the concentration of the copper water complex times the ammonia concentration raised to the 4th power, because there's a 4 in the balanced chemical equation. However, if the reaction was done in an anhydrous solvent or a solvent that does not have any water in it, there is still water present in the reaction itself, but now the amount that is being utilized in the reaction is small enough compared to the rest where you can actually pay attention to it. So if the solvent is not water, Now the water can be included. And this is where solvent selection really plays a role, because if you were using a solvent that's in the reaction in one way or the other, it's really going to change the equilibrium conditions and those equilibrium ratios.
In this reaction, the solvent plays a key role. Because the reaction greatly involves the molecules of water, using pure water as the solvent will influence the reaction. Cobalt chloride hexahydrate solid is a red solid. However, depending on what the solvent is, the color of the solution can vary. Solutions dissolved in water retain the red color. However, if water is not involved and a solvent chosen is not water-based, such as anhydrous ethanol, the solution is a blue color. This blue color is where the term or coloring of cobalt blue comes from. Cobalt chloride in its pure state without water is a blue color, and it's only the presence of water that causes the red color to appear.
So in an anhydrous condition, in that state where you're taking this cobalt chloride hexahydrate and dissolving it in ethanol without any water, you need to know what are the starting concentrations, how much of each of the components is present at the beginning. And this is based on the sample size. So you have cobalt chloride hexahydrate, that's that red powder, and that's being dissolved in ethanol. And because this is a hydrated solid, there is water already contained in that red powder. That's why cobalt chloride hexahydrate is a red powder, where cobalt chloride anhydrous, meaning without water, would be a blue powder. You're starting off with the red powder primarily because it's cheaper. You're going to be obtaining the mass of cobalt chloride, dividing that by the molecular weight, figuring out how many moles of cobalt chloride hexahydrate there are, and then determining how many moles of cobalt ion would that be, how many moles of chloride ion, how many moles of water molecule, and those subsequent molarities which are coming from that solid itself. So in the video, the initial volume is 10 milliliters, and you're adding, or the video adds, 0.800 milliliters for a final volume of 10.8 milliliters. So based on the mass of cobalt chloride, you can figure out the starting concentration of cobalt, the starting concentration of chloride, the starting concentration of water that comes from the cobalt chloride, and then you added water. We added 0.800 milliliters of water, and this was at a temperature of 25 degrees. So the volume of water needs to be converted to a mass of water using the density here. The density is not exactly 1. And once you have the mass of water, you can use the molecular weight and calculate how many moles of added water there was. When you add together the moles of water that was added, plus the moles of water that came in with the cobalt chloride hexahydrate, then you have the total initial moles or initial concentration of water. And you're using the initial concentrations of chloride ion and the initial concentrations of water to figure out overall the equilibrium constant.
The experiment itself involves the preparation of a cobalt chloride solution in ethanol. That is an anhydrous solution. The only water present is that which is brought over from the solid compound. Cobalt chloride hexahydrate has 6 molecules of water for every 1 molecule of the cobalt chloride hexahydrate. By starting with the blue solution of the cobalt tetrachloride complex and adding a very small but known amount of water, the color of the overall solution is a blend. The solution color is a mixture of the blue cobalt tetrachloride and the red cobalt hexaquo color. The result is more of a purple solution. It's this purple solution that would have the color characteristics of both the pure blue cobalt tetrachloride complex and the red cobalt hexaquo complex. If you were to take an absorbance spectrum of either of the pure compounds, you would only see one peak, one primary wavelength of color that absorbs the most. However, using the cobalt, the blend of cobalt tetrachloride and cobalt hexaquo, there are 2 peaks. There are 2 competing molecules and complexes in equilibrium with each other. When these are combined, you get the color scheme of both of them. Using a spectrophotometer, you could obtain the absorbance of each of these different wavelengths and correlate that to a specific concentration of both of the complexes.
So with knowing how much initial chloride and initial water you have, you mix that together with a little bit of additional water, and it went from that dark blue color to more of a purple color. There's an equilibrium occurring. There is both the cobalt chloride, or like the cobalt tetrachloride present, and the cobalt hexaquo complex. So both the blue and the red is present at the same time. Based on the absorbance readings from the blue sample, the cobalt tetrachloride, and the cobalt hexaquo sample, the red component, using the absorbance values, you can figure out the concentrations at equilibrium of the 2 complexes. But to solve for the equilibrium constant, you need to also know the concentrations of the other components, the free-floating chloride and the free-floating water that's still present in the vial. So you know from the initial concentration the total amount of chloride and the total amount of water. This is the initial concentration. It can't be any more than that. some of it is being bound to the cobalt, some of the chloride and some of the water. It's both being bound to that cobalt and taken away. So it's no longer free floating around. There's some of it being bound to the cobalt. So if you subtract these two, then you end up with the total free floating concentration of chloride and free floating concentration of water. So for every one molecule of cobalt tetrachloride, there are 4 chloride ions that were used to create that molecule. For every 1 molecule of cobalt hexaaquo complex, there are 6 water molecules. So you have to account for that using those stoichiometric ratios. And this is where the ICE tables come in and play more of a role. So initially, before the reaction started, there was 0 of either of these complexes. But of course, equilibrium happens, and then you're given the concentrations of these in the unknown. Or if you were to measure these in a lab, this is what you would measure: the concentration, or at least the absorbance, and then convert to a concentration of the blue cobalt tetrachloride and the red cobalt hexaaquo complex. So in either case, if you start it with 0 and now you know the end product, you know that change, you know how much of it was added from 0 to get to that value. And because in the case of cobalt tetrachloride, for every 1 cobalt tetrachloride complex, it contains 4 chlorides. So if you have the initial chloride, that total concentration of all possible chloride present, and you subtract the amount that's contained within the cobalt tetrachloride complex, now you're able to solve for what is that free-floating amount of chloride that's present in the sample. The same can be true with the water. You have the initial water concentration. This is coming from both the sample mass and from the water that was added. So you have that initial water concentration. And for every 1 cobalt hexaaquo complex, 6 of these water molecules are being taken away and used up in that complex. So it's no longer free-floating water. So when you go through and solve for that, you're figuring out what the equilibrium concentration of these, both the chloride and the water, actually are. So when you're using these values, you're using the concentration of the cobalt hexaaquo complex, the concentration of free-floating chloride, the concentration of cobalt tetrachloride complex, and the concentration of free-floating water. These are all at equilibrium, and it's temperature dependent. You can see that when you increase the temperature, it becomes more blue. It becomes more of that bright cobalt blue, so it's making more of the cobalt tetrachloride. When you decrease the temperature, it becomes more red. It's making more of that cobalt hexaaquo complex. So the equilibrium is temperature dependent, and you can look at that and measure from the equilibrium by each of these 3 different temperatures. You look at the equilibrium constant, and from that you can determine the thermodynamic properties of this equilibrium equation.
With the cobalt solution prepared and properly mixed to achieve a blend of both complexes in equilibrium, you can move on to the last part of the experiment, which is the temperature dependence of the reaction. The blend is a purple color, a mixture of the blue tetrachloride complex and the red hexaquo complex. The reaction itself is temperature dependent. By placing the purple blend in an ice mixture for a few minutes or so, the equilibrium shifts to one side. This can be seen because after a few minutes or a couple of seconds, you can see that it's noticeably much more red than it was initially, especially towards the bottom of this test tube. As it's cooling down, the equilibrium shifts and favors the red hexaquo complex. However, if you take this same solution and place it in warm water, the reaction itself shifts to the opposite end of the equilibrium, overall forcing it to go more to the tetrachloride complex and become a blue color. This equilibrium shift can go back and forth depending on the temperature. And overall in this experiment, you're looking at the temperature dependence of this equilibrium reaction by looking at the equilibrium constant at 3 different temperatures and plotting this to figure out the enthalpy and entropy of this reaction.
So you can see how the temperature or the energy of the environment can affect the equilibrium. You can see that in the changing of the color, going from the equilibrium purple, where they're nice and balanced together, the 2 different complexes, and you increase the temperature, it goes more blue. You decrease the temperature, it goes more red. The temperature plays a critical role in the equilibrium. And because of that, you can relate the 2 large concepts in Chem 2 relating equilibrium and thermodynamics based on the energies. And what you're doing is you're going to be plotting a Van 't Hoff plot of cobalt chloride using your data. So for each of the 3 temperatures, you're calculating what is the equilibrium constant. And then when you plot the natural log of the equilibrium constant on the y-axis versus the inverse temperature on the x-axis, this is what's called the Van 't Hoff plot. And it should be a very straight linear line. And from that, you can determine the equation of that straight line. You can just solve for a slope and an intercept value. Now, these are, it is important when you're making the Van 't Hoff plot, the temperature does need to be in Kelvin. So it's 1 over the temperature in Kelvin. And the equilibrium constant, you're looking at the natural log. So this is ln of the equilibrium constant. And you're going through and plotting this to solve for both the slope and the intercept value in this straight line. So the slope and intercept of that value, or of that line, are related directly to the thermodynamics of that equilibrium equation. So the slope is related to the enthalpy value. The slope is equal to negative delta H over R, so the gas constant, and the intercept is related to the entropy, so delta S over R. And from these equations, from that slope and from that intercept, you can calculate the enthalpy, you can calculate the entropy, and you can, using that and the different temperatures, you can solve for delta G and get the Gibbs free energy for these different equations, and also figure out at what temperature does this reaction become spontaneous? At which temperature will it actually go from red to blue or blue to red? What is that final temperature?
This experiment combines a number of different concepts that you've gone over in Chemistry 2. It's taking an equilibrium reaction, which is prepared using different moles and different ratios, and you're determining the equilibrium of this at different temperatures. You're looking at the ratio of product and reactant at these different temperatures, and from the change in the equilibrium constant, you can then calculate the enthalpy and entropy, and overall you can see at what temperature would this reaction become spontaneous. It's relating the two very important concepts of equilibrium and thermodynamics to show that many times in all of these reactions there is an equilibrium, but there is also the thermodynamic data and the thermodynamic properties of these different reactions that are always there in the background. It's relating these two concepts, and as you go through this and look at all of the different observations and calculate those different equilibrium constants and thermodynamic properties, you'll get a better sense of how these types of very different chemistry concepts can be related in chemical reactions.